So in this video, I'll be talking about how you get the steady state for two spherical tanks of different heights with the fluid flowing. So let's draw the tanks. Tank 1, some height. Tank 2 with some lower height. H2. H1. Some is flowing in here, and some is flowing out. So we say Q and 2 there, Q and 1 there, and let's see if I can make this a different color. Yeah. So it's the area, different tanks, and you got the flow rates and the velocity. Well, first we'll talk about the velocity. We got V1, V2, V1, 2. And now, after we got that, we actually do want to find the flow rates now. For so Q1 is equal to V12 A1. Q2 is equal to V2 A2. But we don't have the velocities, but we can solve that. So as I scroll down, you know that pressure is equal to rho GH. And we also can set this up to a differential, or just an equation. You know that pressure 2, so a balance equation is pressure 1 over the density minus gravity of C1 minus C2 minus E2 squared P1 squared over 2 is equal to 0. Now, to get what we need, let's go back up to the top. We'll say this is point 2, this is point 1. Due to these, let's say, point 1 and 2 are the same height, which means this here is just going to equal 0. As we further look, this is in a large area, so point 1 is going to have velocity of 0 for that. As we see, P2 is going to be gauge pressure, or not P2, that's my bad. P2 is going to read the pressure. P1 is not, it's in a large cross-sectional area, gauge pressure. Absolute, it's not going to change. P2 will be equal to something. P1 will be equal to 0. So as we do this, we get P. So as we had here, say P is equal to rho GH. So rho GH. Rho cancels. All that cancels. Plus V2 squared over 2 is equal to 0. Now to find the velocity, you can just move out to the other side. So you'll get V2 is equal to radical 2 G change in height, so it'll be H1 minus H2 in this instance. But when I look at that, the signs are not adding up. I made a mistake. That P1 is not equal to P0. It's P2 is equal to P0. Let's see what my explanation was there. It's going to be outside. Okay, so there's going to be no pressure on the outside as it flows out. And then there will be a pressure due to the area. So this will be a negative. We move that to the other side. It'll be positive. Okay, that makes sense. So we got a velocity now as we continue. And now we got Q1, V12, and V2. And what we were going to say now, density is constant. So water's going to be flowing out of tank 1 into tank 2. Or fluid, doesn't have to be water. And then fluid also is going to be coming out of tank 2. So we want to get this in terms of volume now. So dV1 over dt. So this is over time now. It's going to equal to, let's see, the picture. So a bit better if you remember. Okay. So the flow of 1 or in 1 minus V2. Well, we had that, so we're going to have U2G H. Well, not we need absolute value, because if that's negative, you can't do it. And to make sure we do have this as the right sign, say S sign of H1 is H2. And for tank 2, volume, let's make that better T. Volume of 2, as it changes with time, of Q in 2 plus, since water is flowing in to tank 2 from tank 1, we have plus what we had there, G. So the value of H1 is H2. You have to do the sign again, so sign H1 minus H2, so we can get it. Tank water is also going to be flowing out of tank 2. So we're going to have minus radical 2G H2. And I forgot something. Let's see. Area. Yeah. Since Q2, yep. This is going to be the area of 1 to 2. You're going to be the area of 2. Let's see, you're going to be the area of 1 to 2, and that's going to be, both those are multiplied. Yeah, move forward. EV1 or dt is going to equal to the area of said tank, C1, for the height at tank over T. So now again, we got height now as a contributing major factor. dV2, it's going to be the same thing, just different area and different height. And this is going to come in handy when we do our differential equations. So when we're at a steady state is what we're trying to find. Steady state 0. So we can set these equations up there equal to 0. So equal to 0 equal to both these equations up here. And that should give us what it would be in a steady state. For the differential equations, as I said before, let's use, I'm not going to use the bar. We have these, but it's now, we're going to say, it's going to be equal to, now we're going to use flow rates. So volume 1, you're going to have Qn 1 minus Q12. I believe that's what we labeled it at the top. And V12, so we can say Q12. And for D V2 dt, you're going to have Q2n plus Q12 minus Q2. And this is supposed to be Q12. I said it's not going to be dV anymore. Erase that. That was, we keep carrying over. That's what we're gonna have. Area. So I'm erasing most of area. Tank 1. Area of tank 2. And now we have the differential height that is changing over time. And this is the differential equations that we're going to need to solve for the spherical tanks changing in height and the fluid height to solve the equation. When you derive this, you just move dt to the other side. You'll have a t eventually on all these, because it's going to be, the flow rate at the time is going to affect how the height goes as well. So you'll have height changing. You'll get a height over here with the area, because that is also going to be changing. Well, not area 1 of the tank, but the height of the fluid will. And the time, the flow rate will change with time. And now we can go on to the next step, which will be coding this with actual numbers that are going to be given to us.